Welcome to section 6 of chapter 9, Exponential Growth and Decay. We're going to go back to what we did in the first section. We're going to add on it, we're going to build on it, and then we're also going to take a look at some formulas that represent growth and decay. So this is similar to a graph that you've seen in section 1. This is a decay model because it starts at the left and it ends up going down. This is a pizza problem. It's price per square inch on the y-axis and the diameter in inches. So what it's saying is as the diameter gets larger, as it moves to the right, the price per square inch actually goes down. So what I want you to consider here is, will the price per square inch ever be $0? It won't. In fact, it'll max out, and if you continue to keep going this way, it'll get really close, but it'll never quite get there. And what we call this is, we call this an asymptote. It's basically a line that the graph gets really, really close to, but it never quite gets there. This is a description that they show sometimes. It's from MC Hammer. It's called "Can't Touch This." So it's a line right here, and notice that this piece gets infinitely close to it. It gets very, very close, but never quite gets there. If this is a growth model and it's like this, then sometimes our asymptote will be right here. Okay, so this value is something that it'll never quite get there, but it'll get really, really close. In this pizza example, you want to eat an entire pizza, but you're going to start by eating half the first day, and then the next day you're going to eat half of that half, and then the third day you're going to eat half of what's left, and you're going to keep going in this pattern until the pizza's all the way gone. What day will you finish the pizza? You actually will never finish the pizza if you look at it this way, because once you start with a full pizza on the first day, the second day you have half of it left, the third day you have a fourth of it left, because a half of a half is a fourth. The fourth day you have 1/8 of it left. The fifth day you have 1/16 of it left. The sixth day you have 1/32, and you continue and continue, but you get so close to 0. If you estimated these values, you would keep going lower and lower. You keep getting closer and closer to 0, but you would never quite get there. That's what we call an asymptote. I want you to skip over the next 2 slides at this point, and now we're going to go to the exponential decay slide. Okay, so exponential decay. This formula right here will be used. It'll be used for growth and decay. Notice that there is a plus and a minus. If we're looking at decay, we are going to use the minus side. Okay, so in these problems, it'll give you this model, and you have to first decide: is it growth, is it decay, and which one am I going to use? So this decay one is actually going to be 1 minus r to the t. So now what do these variables mean? A is your initial amount. Okay, whatever you started with. That's what your A value is going to be. R is going to be your rate. So R for rate, that's going to be either a decay rate or a growth rate, depending on what the problem is. And T is going to be your time. So what we're going to be doing on these problems, we're going to be identifying what are these variables, which one are we looking for, and then how can we solve for it. Exponential growth, and notice it is the exact same formula, except this time we are getting bigger, so we're going to be adding it. So this formula is really 1 plus r to the t. A is still the initial amount, or what we start with. R is still our rate, and t is still time. Okay, so those are 2 growth and decay formulas. Here's a reference slide that'll be really helpful. Here, just kind of put all together decay and growth. If you notice, there's a couple of other formulas that we're going to use here. Let's just identify them really quick and what these are going to look like. Okay, this second formula is actually one that scientists use a lot, and it's just a more accurate model. And it's one that they prefer. So here your A is still your initial amount. E is, as you know, is a number. This K is going to be a constant. They're gonna tell you what it is. Okay, T is still time, and then A is still your initial. So we're going to use these the same way that we would this other model. It just really depends on the type of problem. But really think about when you're given science problems. These are ones being given. And one thing I didn't mention yet was this Y. This Y is what you end up with. Y is your final. Okay, so we have an initial, we have a final. Same thing here. This Y is the final. It's what we end up with. Alright, so here's our basic growth and decay slides. Let's go ahead and knock out a couple of other types of problems that you might see. So here is a compounding. It says n amount of times per year. We're going to use this formula. So if it gives you a problem and it says we put this money in a bank account, it compounds 12 times a year. What's the final amount? Okay, let's go through a few of what these variables mean. T is always time. R is always the rate of growth, or the growth rate, whatever you prefer. P is what we call the principal, and principal is the money invested. Okay, it's how much you started with. Okay, and then A is your final amount that you end up with. So you put money into a bank account, it compounds a certain amount of times, and then you get the final amount out. That is what A means. And notice final amount. Alright, so that's compounding n times per year. And the last one we're going to look at is the continuous compounding. So P is still principal. Notice a lot of these are staying the same. We're not changing it up. And that's, again, money invested. R is your rate of growth. This could also be called the interest rate. T is time, and A is your amount that you receive. All right, so let's do some examples. Before we do any examples, check out some of these example keys that I give. These are the things that really help me out. I identify what formula is going to be given, or what formula we're going to use, rather. It's usually given. I identify what variables we have and which ones we're trying to solve, and then I plug in the given values and solve for the one that I don't know. Alright, so here we go. The Addams family bought a new house 10 years ago for a certain amount. Okay, so they give us a formula. It's now worth this much. Steady rate of growth tells us that we're going to use a plus sign because it's growth. The yearly rate of appreciation. This rate, that's still R. So we're looking for R. T was 10 years. The house is now worth 140. That means that the final amount that it's worth is 140. And we initially invested A. Or we initially spent A. So now we have our numbers, we plug them in. Okay, so I systematically plugged each of these variables in. Now we want to solve for R. Before we can solve for R, we have to get this piece by itself, so then we can 10th root it. So we're going to start by dividing by 80,000. And we're going to do it to both sides. Okay, when we do, we end up with 7 over 4 equals, this piece goes out, and it's 1 plus R to the 10th. Okay, so now what we want to do is we want to do the 10th root of both sides to get rid of this 10th. So now we have, and I'm leaving this all for computations at the end, 1 plus R. And now what we're going to end up with is subtracting 1. So we're going to have the 10th root of 7/4 minus 1 equals R. So plugging that into my calculator, I find it to be, my R to be 2.72. Now Alright, let's go to our next example. It says, in chemistry, we're looking at radioactive material and it's going down, it's decreasing at a certain rate. It's telling you what formula to use. And notice that they tell us the K value. So I always write out what I have. So I have this K value, 500 grams. That's my initial. Okay, my final, I want to reduce it to 200, so that means our final is going to be 200. And now, what are we trying to find? Okay, we're trying to find T. So if we don't know what T is, we obviously can't plug anything in for it, but we can plug in our other values. We say 200 is equal to our initial, and it's e to the, our K value was negative 0.377, and then our time, we don't know what it is. Alright, so now that we've plugged it in, now it comes down to solving this problem like we have in the past. So before we can solve for T, we have to get this e to the exponent by itself, so we want to divide by 500. We end up with 2/5 is equal to e to the negative 3.77 T. Now we want to do the natural log of both sides because we want to do that inverse operation. So we have natural log of 2/5, and that equals negative 0.377 T, these two inverse operations. Now we're going to divide by negative 0.377. And we get our T value to be approximately 2.43 days. So a couple things to consider. Time will always be positive. So if you plug these items in and you get a negative T, you did something wrong. T should always be positive because you can't measure T. You can't say, oh, it was negative 2 days. It doesn't really work like that. We always have to say T is positive. And does this seem realistic? Yeah, it does, because we went from 500 to 200, pretty decently high K value, rate of decay. So yes, it does seem reasonable. This will be the last example that we do on this page. This is talking about police using the blood alcohol content to measure basically how able you are to drive. If you're above a certain BAC, then you're not allowed to drive in the state of Missouri. And that's 0.08 in the state of Missouri, and that's where it is most places as well. So we're going to use a similar format. They're going to tell us what to do, what formula to use here. Alright, so if we're talking about BAC starting at a certain point and going down, we are talking about a decay model. So we are going to use a 1 minus R to the T, and now we have to identify what's given. Okay, so each hour it may decrease by 15%, so that means our rate is 0.15. And another thing, whenever we're given rate, we always want to put it as a decimal, no matter what. So if they have a BAC of 0.18, that's what they're starting with. So A is 0.18. What do they want to get to? Their final? It has to be 0.08 in order to drive. And now we're looking at time is what we're trying to find. So what I'm going to do is I'm going to take these and I'm going to plug. Okay, so the first thing I'm going to do is I'm just going to simplify what's in here. I'm going to say it's 0.85, and that's to the T. 0.18 stays the same. And now I want to divide both sides by 0.18. And now we know that we're not going to be able to get these bases the same, so what we can do is we can do the log of both sides. So we have log of 0.444, and that equals log of 0.85 to the T. We can move this T to the front and divide by log of 0.85 to get our final answer. To get our approximate answer of 4.99, or we can round that to 5 hours. Okay, what I want you to do is I want you to complete the next two examples. I'm going to make videos and I will post those solutions.